The first thing we're going to look at when we were talking about power functions and function operations is simply just a warm-up to try to get an idea of what kind of operations we're working with. If you notice, a lot of these things of the past, and in chapter 6 we work with adding and subtracting polynomials, we're doing that in a much simpler sense. Our functions that we're going to be operating with are definitely as simple as what you see in front of you. So let's take a second and do this warm-up, and we'll get more into what we're doing later. Just a quick note, though, a couple of key ideas about this. This is going to be one video, a very long video. I'd say probably about 10 minutes. That's my goal, to make it 10 or less. But it is the entire section. So you can watch it multiple times, watch it one time through, or just freeze frame each slide to take the notes and just hear me talking it through. That's my advice, is to just allow yourself to just listen rather than constantly have to worry about jotting the notes down to catch up, because you can always rewind it. So let's look at the first example. All we want to do there is distribute the 4 to each of the two terms. So it's x squared plus 1, where we distribute the 4 being 4x plus 4. The second one, we have x minus 2 plus x squared plus 1. You're simply adding polynomials. So in that case, there's only one thing that combines, which is negative 2 and 1, ends up being a negative 1. The next one, there's going to be a typo, so I'll have to correct it before you even can identify it. If you distribute this negative here, you're going to distribute this negative. That's very crucial. Distributing that ends up being negative x squared minus x. Cross that out, and then we'll replace that with a negative x minus 3, because it ends up being negative 2 minus 1. Down here, we are foiling this one, or distributing, however you prefer to view it. So that ends up being x times x, or x squared. And then the next one is plus x minus 2x, which is where this negative 1x comes from. And this is actually a 2, so it's negative 2 times a positive 1. That's a great 2. Look at number 5. We're evaluating now. It's function notation. We're saying, okay, if I take this 2 and plug that in, if I take this and plug it in right here, what is this function going to look like? In other words, it's 3 times 2 to the second power minus 5, or 3 times 4, or 12 minus 5, ended up being f of 2, which is equal to 7. Just a little warm-up to kind of give us an idea what we're getting ourselves into. Now let's start with part A. So this is operations. I guess we could cross this out and say of functions, not on. Technically they're okay, but of sounds much better. So operations of functions. Let's take a look. So first we have this big chart here where we have the operation to the left, the definition at the beginning, which this is just technical notation in the middle. And these examples are crucial. Right here, all of them are stemming from what this x minus 1 and this 3x are. So f of x is x minus 1, which is one of the functions. The second function is 3x. So when we operate in the first one, all we're simply doing here is we're adding the two together. That's where this comes into play right here. No multiplication, no nothing. So in this case, 3x plus x is 4x minus 1, and that's it. That's all you need for the first one. The second one, very similar. We're going to subtract them in this case, distribute this negative here. So that's negative 3x plus x, or negative 2x minus 1, as it says. In multiplication, this one's a little trickier. You have to make sure that you distribute the 3x, or distribute each of these terms to 3x. However you view that, you're going to get the exact same value. So you get 3x squared minus 3x. We know from before that factoring this one out, we would take a 3x out of both, which is exactly what is shown right here. Lastly, the division, which is going to give us the most problems in general, and very much so specifically when it comes to the domains. We'll talk about that shortly. So this is x minus 1 over 3x, and you can't simplify any further. You cannot cross these x's off like you might be tempted. This is, I promise, the final answer for this function. Okay, something important to note on the side. A power function, with the section title is power function, the function operation. A power function is simply y equals ax to the b. This is the b. This b is the exponent, okay? This a is a real number, and b is a rational number. No longer does it have to be 1, 2, 3. Those are all nice, because that's a linear function, a quadratic, a cubic, a quartic, and so on. In this case now, it could be, y equals 2x to the 1/4, something to that effect. It does not have to be 2x to the 4th anymore. So let's take a look at how we operate with functions. An example, we have here example number 1. We want to look at f of x, which is equal to 3x to the 1/3. So the only thing to the 1/3, technically, if you really want to get tricky with this, is just x to the 1/3. That 3 has no affiliation necessarily with that 1/3. And then this over here. So in other words, if you were to operate, you would. But in terms of how we're going to separate this, you're going to see how it actually helps to put it all as one. So we're going to do two things. We're going to first look at the sum difference of the functions, and then look at the product quotient of the functions. So the sum of the functions, you pretty much just say f of x plus g of x is the two added together. Well, it's not as simple as saying x plus 2x is 3x. It's not that simple, but it almost is. So if you look, you want to say, okay, they have this term is exactly the same. So like we said before, you're almost technically anti-factoring. So you're taking a step backwards and saying, okay, you could say this is 3x and this is 2x all in this 1/3. You technically could, but that necessarily wouldn't be right because that means that that 1/3 would then be distributed to the 2 and the 3. So in other words, you're only looking at factoring 3 and 2 out of both of these, which then it's as simple as adding the two together and writing it as 5x to the 1/3. The second one, we look at the subtraction of the two. So it's a very similar setup. You can see it again. We have this thing in common. So you can rewrite it, in this case, 3 minus 2, or it's just simply x to the 1/3. So no real tricks there. The major difference being that you write the 5 here and you don't write this understood 1. Now the product quotient's a little trickier, the function. If we look at the product first, that's f of x times g of x. Again, so it's just showing it as multiplication rather than these obviously doing addition and subtraction up here. So if we look at the multiplication, you do it very similar, except now you can rewrite it in this sense, where now you're adding those exponents. By multiplying these first, we come up with a value, which we'll note here in a second, which is obviously going to be 6. But we then know if you rewrote this, you could write 3 times 2, and then x to the third times x to the third. Well, if you know they have the exact same base, both being x, that's the same as saying x to the 1/3 plus 1/3, or x to the 2/3. This ends up simplifying to be 6 coming from here, obviously. And then 2/3 comes from 1/3. This is a little trickier. It's going to be a little cut off down there. This is a 2x to the 1/3, very bottom. But if you look at f of x over g of x, is showing them as division. But we know, unlike in multiplication, when you add the exponents, we're going to subtract them. So you do 3 over 2 first. Unlike 3 times 2, which is nice and easy number 6, 3 over 2 doesn't come out as clean. We can see that x to the 1/3 minus 1/3, this ends up just being x to the 0, unfortunately. So x to the 0 is just 1, or in this case, it's going to be equal to just what we have left over here, which is 3/2. This is where this obviously stems from. Now, what about the domain of each function operation? Domain operating in terms of looking at the x values that are possible, because we are only looking at x for the time being. So if we look at what the possibilities are, we see that these are the two functions, which we'll definitely go over this in much more detail, and the book clears this up for you if need be. If we look, the note we have f of x and g of x have the same domain, all real numbers. If you were to graph those, you would see that it would incorporate all potential x in what, all positive and negative x values. So if we look, talk about end behavior, it's very similar to this in terms of how we refer to it, but we're lumping it all into one statement. The domain is talking all real numbers could possibly be values of x. In this case, that means the domain of f of x plus g of x is equal to f of x minus g of x, which also both are all real numbers. So both this function operation and this function operation are all including of all real numbers. If we look, consider the domains of the product and the quotient of the functions. If we look at the first one, the domain of f of x times g of x is all real numbers, because the answer, if you go back a second, 6x to the 2/3 incorporates all kinds of values as well, both positive and negative. So again, all real numbers are possibilities for x. Although the domain of f of x over g of x is all positive real numbers, and just do this for me. Just make a big box over that one, and just refer to that as something we will definitely cover before we take the mini quiz. There are a few things we need to cover. So anyway, all positive real numbers is the domain of f of x over g of x. Okay, so let's look at part B then. Part B, we're taking the composition of two functions. The composition of a function, f, and the function g is. It's written a little goofy. It's f h of x is equal to f of g of x. So instead of just this in here being simply an x, now it's the entire function of g of x, which you're evaluating. So this part right here, I'm just going to add a little star, hold on, a little star over here, because this is crucial of understanding. So let's look at the domain of g. So it's saying where the domain of h is the h of x, up here. Domain of g, the input of g over here. When evaluated as g of x takes the output of g, considering this, and considering the input of f, all equal to f of g of x, which is another, doesn't really matter, there should be a parenthesis there. which is the output of f, or the range of f. So you can see the domain of G and the range of G, and the domain of f and the range of f. So in other words, it might not make sense at the moment, but we're definitely going to cover this in more detail tomorrow as well, taking a better look at how we can decipher this. We're going to give, so there are some examples here, but we'll look in a little closer. So find the composition of functions. So we want to, example 2, we're going to look closely at, given these two functions, 2x squared minus 1, we want to find f of g of x, g of f of x, and so let's look at this. F of g of x is equal to f of x squared minus 1. So this used to simply just say f of x. In other words, I said, what if I said x was 2? You'd plug in 2 for this function right here. That'd be 2 times 2 to the negative 1, or 2 over 2, or 1. Right? So that was what we'd done before. But now we're evaluating the entire thing. Evaluating the entire thing, we take this idea right here, this x value, and we plug the entire function of g of x right there and evaluate it. So then you just evaluate. So that becomes 2 times. So we know this entire thing. Let's cut it off right here. This entire thing to the negative 1 is all going to go to the denominator. So that's the same as saying 2 times 1 over this entire thing. The 2 does not get lumped into that because that has nothing to do with this exponent. So in that case, you multiply 2 times 1, or 2 over x squared minus 1, which isn't all that bad. The next one, if you look at g of f of x is equal to g of 2x to the negative 1. So we're evaluating this x right here with this value of x, or in that entire function for that matter. So that's rewritten as 2x to the negative 1, all to the second power. You want to distribute that 2 to both. In other words, you want to say 2 to the 2, this 2 gets distributed to this negative 1, and all the way over to the 2. So that's 2 to the 2. I went ahead and took a step and said, look at this negative 1. I'm going to put it in the denominator as a positive exponent, all minus 1. And 1 does not have anything going on here. We leave it as is. In that case, that just ends up being 4 over x squared minus 1. You could eventually combine those. We don't know how to do that. We're going to leave that for the time being. Lastly, let's look at the domains of those two separate things. I'm just going to throw them up there, and we want to refer back to them tomorrow. So the first one, the domain of f of g of x is all real numbers except when x is 1 or when x is negative 1. In other words, when I plug in x is 1 or x is negative 1, the denominator becomes 0, which is not part of our domain. We'll talk about why that's undefined. We've mentioned that term before. We haven't covered it in a while, so we'll come back to that. Lastly, the domain of g of f of x is all real numbers except when x is equal to 0. Exactly. So we had 4 over x squared. If that x squared is, if x is 0, that's 4 over 0. And again, that's undefined. So these two are defined by what makes the function undefined, which we'll cover that again a little closely tomorrow in class. I know there's a lot of material. I know, oh gosh, we're 13 minutes. Nonetheless, give it a chance, look it over, watch it again tomorrow if necessary, and we'll go over the quiz midway through the class tomorrow. Okay, thank you. Hope this helped, and good luck with reviewing.